All right, guys, so here is our video for 5.4, which has to do with complex numbers. And they are a little bit complex, more new than anything. But before we go into complex numbers, I like to do a quick sort of pre-lesson, just reminding you of some really basic square root properties that you've seen before, that you know, and need to know how to simplify square roots. That's going to be huge for complex numbers. So square root of 96, there are lots of different ways to simplify this. The one that I'm kind of partial to is the tree method, and some of you have probably seen this before. But the idea is we need to break this up into two numbers that multiply to be 96. It's even, so I'm going to say 2 times 48. And I broke up 96. So I can't break 2 into anything other than 2 and 1, which doesn't really simplify because we still have a 2. So I'm going to leave that left-hand branch alone. I'm going to break 48 into 6 times 8. And now I'm done with 48. And I can break 6 a little bit further. How about 2 and 3? So 6 is done. I can break 8 into 2 and 4. And I can break 4 into 2 and 2. And what I'm left with in this tree is the prime factorization, all the prime factors, 2 times 2 times 3 times 2 times 2 times 2, that will give me 96 at the end of the day. So how does this help me simplify that square root? Well, it's a square root. I'm going to look for pairs. I've got 2 2s here. I've got 2 2s here. And then I've got this leftover 3 that doesn't have a pair, and this leftover 2 that doesn't have a pair. He was kind of the odd man out. So here's what this means. If I find pairs inside my square root, I can pull them outside. So I had a 2, I had another 2 that I can pull outside. So I'm going to multiply those together. And I'm going to multiply together inside the square root whatever was left over, the 3 and the 2. And so what does this equal? This equals 4 root 6. Simplifying a square root. Let's try another one. 40x to the 5th inside that square root. So I'm going to start with just the number part. 40, I could say, is 4 times 10. 4 is 2 times 2. 10 is 2 times 5. And I can't break any of those down. Those are prime numbers. So do I have any pairs? Yes, I do. I have a 2, so I can pull it out. And it looks like I'm going to be left with a 2 and a 5 inside. So I know I'm going to multiply them. 2 times 5 is 10. So notice when we find a pair, only one of the numbers gets to come out. The pair only counts for 1. That's why we only had 1 2 here. Okay, but what about that x to the 5th? So I got to think to myself, and you won't have to draw a tree for this every time, but x to the 5th is x times x times x times x times x, right? Well, do I have any pairs? 1 pair, 2 pairs, with 1x left over inside. So I'm going to put that 1x left over inside, and I pull my 2 pairs of x's out. So that's x times x, x squared, 2x squared root 10x. Last one I want to kind of go through right now, square root of 32 over 81. Well, step 1 is whenever we're doing a square root of a fraction, we can, if we want, always do this. We can break it up into square root of the top over square root of the bottom. Now, square root of the bottom is kind of easy. What's square root of 81? 9. And what about, though, 32? I'm going to take 32 and break it down. 4 times 8, 2 times 2, 2 times 4, 2 times 2. So again, break it down into its prime factors. And I'm going to say, okay, I have a pair of 2s. I have another pair of 2s. I can pull out 2 2s. So that's 4, 2 times 2. And then I have the 2 left over inside. 4 root 2 over 9. And I'll put that in purple just to make it match. 4 root 2 over 9. I know I went through some of this kind of quickly, but that's because you have seen this before. You should be somewhat familiar with simplifying square roots. If not a problem, unless you don't say anything. If not, let me know so I can help you, assist you, teach you this stuff, and then give you a little bit of extra practice. I'm not trying to give you more work, but just practice so you feel confident. And then you'll be ready to go with these square root properties. But where are we? Okay, well, let's just do some practice with square roots before getting to complex numbers. Simplify root 64. Check this out. I know that 64 is 8 and 8. Now I could keep breaking down 8s, or I could just say, hey, look, that's 8. I have a pair of 8s there. So square root of 64 is 8. And we know that. Some of you might be saying, though, what about plus or minus 8? Because wouldn't negative 8 squared also equal 64? And the answer is yes. This is where it gets a little bit confusing whether we're just taking the principal positive root or if we're taking both, because technically all of these are plus or minus. So the answer is going to change a little bit through the year depending on what we're doing, the context. But for now, I do want you to realize every square root is going to be plus or minus. And so I'm going to add a plus or minus to each of these and say, okay, anytime I'm taking a square root, it's going to be plus or minus. There will be a positive version and a negative version. What about the square root of 36 over 49? Well, step 1, square root of the top over square root of the bottom. Plus or minus square root of 36 is 6 over square root of 49 is 7, plus or minus 6/7. A little bit trickier. 60 breaks into 6 and 10, which is 2 and 3, and 2 and 5. Do I have any pairs? They're not next to each other, but I do have this pair of 2s that I can pull out. So I'm going to say plus or minus 2. I'm left with a 3 times 5 inside, so left with a 15. And then what about x squared? Remember, x squared is x times x. And that's a pair. I can pull an x out and have nothing left over. Plus or minus 2x root 15. Again, I do know I'm going through this quickly. Hopefully you feel okay about this coming in, and it's kind of making sense. Feel free to slow it down and rewind if you need, or ask me questions. 98 is 2 times 49, and 49 is 7 times 7. That's a good sign. So I can say plus or minus, pull out a 7. I know I'm going to be left with a 2 inside. And then x to the 5th, I have 5 x's. I don't want to write it down every time. So here's what I'm going to do. I'm going to say I've got 5 x's. These 2 are a pair. These 2 are a pair. And we have 1 left over, right? So that means I can pull out 2 x's because I had 2 pairs with 1 left over, plus or minus 7x squared root 2x. Okay, so 2 more, and then we're going on to complex numbers. 288, 2 times 144. I like dividing even numbers just by 2, especially when I get 12 and 12. I could keep breaking them down, but I might as well just save myself some time and say I found a pair. Plus or minus 12 with I had a 2 left over, so root 2, and x to the 4th. There are 4 x's. I need looking for pairs. Here's a pair. There's a pair. I have 2 pairs of x's, so I can pull out 2 x's. Nothing left over. Plus or minus 12x squared root 2. Finally, last one of these. Square root of 48x squared over square root of 25. Okay, so I know it'll be 5 on bottom. Plus or minus something over 5. 48, what does 48 break into? Well, 6 and 8 we could use. 2 and 3, 2 and 4, 2 and 2. We're just breaking them down until we get to primes. Pair of 2s and pair of 2s. So I have 2 pairs of 2s. So I can bring them both out, multiply them. That gives me 4. I'm going to have a root 3 left on the inside because I had that leftover 3 in my tree. And what about x squared? I've got 2 x's. That's just 1 pair that I can pull out. Plus or minus 4x root 3 over 5. Guys, you did this in Algebra 1, 2. You did this in geometry. And so this is, I don't want to say it's assumed that you know this. I didn't assume it because that's why I went over all this. But you should kind of have some idea of how to do this. And as we're doing more and more, it should come back really well. If you're struggling, please let me know so I can just sit down with you for 5-10 minutes, do a bunch of repetition, and it'll help tremendously. But that's going to bring us to our main topic for today, which is complex numbers and imaginary numbers. First thing we got to talk about is the imaginary unit. And the imaginary unit is given its own letter reserved in the mathematical alphabet to represent an imaginary unit. What is I? I is the square root of -1. You might be thinking to yourself, wait, math teachers in the past have told me you can't take a square root of a negative number. You can. They lied to you. They lied to you because you were not ready for the truth, but now you're ready. Now you're ready. So the imaginary unit is the square root of -1. And I kind of hate that name. It's not imaginary, but it's just a different way of thinking about this number and a different almost plane of numbers. So now we can take the square root of a -1. Why did this come about? Well, mathematicians were saying to themselves, man, we can do all this awesome stuff with math, but it would be awesome if we could take square roots of negatives. We could do so much more. And someone came up and said, well, why can't we? Let's do it. And the other people said, well, yeah, but square root means something times itself has to equal -1. So like 1 times 1 equals +1, and -1 times -1 equals +1. So we can never get a negative when we square something. And the first person said, leave it to me. I'll just make up a new imaginary unit, I. And we're going to say that I times I equals -1. In other words, I squared equals -1, which means we could square root both sides and just say that the square root of -1 is I. So that's kind of a long-winded explanation as to what I is, how it came about. And I kind of answered the second question in my explanation. If I is root -1, what is I squared? Well, I squared then would be root -1 squared. And what is a square root squared? Square root squared are inverses, so they cancel each other out, leaving us with just -1. I squared is -1. This is kind of curious. I is an imaginary number. But I squared is a very real number. I squared is -1. So that's the first thing we're going to look at. I've got this beautifully crafted table, and we're going to simplify some i's. Okay, so you'll want to draw this table in your notes just to reinforce this concept, but I is as simple as you get. I is just I. Can't get much simpler. I is the square root of -1, it's just I. What was I squared? Well, I squared, we set up there, is the square root of -1 squared, which means it's just -1. Which then begs the question, what is I cubed? So here's what I want you to see if you agree with me here. Sorry. I cubed equals I squared times I, right? It's like x's. X squared times x is x cubed. I squared times I is I cubed. Well, we know what these two are. -1 times, just I was our simplified version of I to the first. -I. Because it's just I squared times I. So I cubed can be simplified to just -I to the first. What about I to the fourth then? Well, I to the fourth is equal to I squared times I squared. So -1 times -1, and we know what that is. -1 times -1 is +1. I to the fourth is +1. I don't know how I feel about this because I'm like yo-yoing between, bouncing back and forth. I'm going to highlight them. Imaginary, real, imaginary, real. So this is kind of a weird result, if you will. We're just, every time we multiply by another I, it bounces back and forth between imaginary and real. Now check out what's going to happen with I to the fifth and the rest of the way, in all honesty. I to the fifth is equal to I to the fourth times I. What is I to the fourth? 1. 1 times I is just I, right? So the I to the fourth didn't really make an impact because it's just one times another I. Okay, great. So let's go on to, how about I to the sixth? I to the sixth, I could rewrite as I to the fourth times I squared, which I to the fourth is just one times I squared is I squared, which we said earlier, I squared was -1. And you're gonna start to see something here. You're gonna start to see this repeating pattern. Look, I -1, -I1, I -1. Let's think to ourselves about I to the seventh. Here's my I to the seventh. Here are my 7 i's. Well, we know that I to the fourth is just 1. So it's 1 times I cubed. So we don't really need that 1 times. 1 times doesn't affect it. And what did I cubed simplify to? -I. What about I to the eighth? I to the eighth is equal to I to the fourth times I to the fourth. 1 times 1, 1. And you can see that this pattern repeats. I -1, -I1. I -1, -I1. So the next one, I to the ninth, is probably going to be I. So then here's my question. What is I to the 37th power? Now we know it repeats, but I don't really want to count all the way up I to the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th. I don't want to have to count up all the way to 37 or 83 or 4,000 as you see in the table. But here's what I do know. I'm going to change colors in my highlighter. Every multiple of 4, I to the fourth, I to the eighth, I to the 12th, I to the 16th, because of this pattern, they're all going to be 1. So I just have to think to myself, okay, I to the 4, 8, 12, 16, 20, 24, 28, 32, 36. I to the 36th is 1 because it's a multiple of 4, 36. So I'm going to look at this and say I to the 37th is equal to I to the 36th times I to the first. And I know that that I to the 36th is not going to make a difference. It's just 1 a bunch of times. 1 times 1 times 1 times 1. I to the 37th is just I. So this is our general strategy. We're going to look for the nearest multiple of 4 and rewrite our power based on that multiple of 4 plus whatever's left over. And if we do that, these will become much easier problems. I to the 83rd. Multiple of 4, if you're thinking, okay, what's a multiple of 4? How about 80? 4 times 20 is 80. So this is I to the 80th times I cubed. And that I to the 80th doesn't do anything because it's a multiple of 4, that power. So this is just I cubed, which we said earlier in our table, -I. And this is why it's fair game for me to ask you on a quiz or a test, what is I to the 83rd? What is I to the 4,000th? Well, you might notice 4,000 is a multiple of 4, right? Any multiple of 4 as your power for I is just 1. I to the 4,000th is 1. So I'm throwing a lot of new stuff at you, complex numbers. But what good are they? Well, now we can do these types of things. We're going to kind of crank through some problems. What is the square root of -25? Before today, you would have said, can't take a square root of a negative number, come on. Now, however, we know we can. I know that I could break this into -1 and 25. Now, 25 is 5 and 5, and there's my pair. Found it. So I can pull a 5 out. I know it's plus or minus. I can pull a 5 out, and I'm left with the square root of -1 because there was no pair for that square root of -1. But you know what? I don't want to write square root of -1. That muddies things up. I have a cleaner way to write that. Plus or minus 5i is the square root of -25. So something you can remember is any of these radical problems that we have, if it's square root of a negative, you're always just going to have an I outside. You're going to pull an I out. Quick pop quiz. What is I to the 8th? And I'm hoping you're thinking to yourself, okay, so that's a multiple of 4. So that means it's 1. Multiples of 4 are always 1. All right, square root of negative 72x. Okay, so it's plus or minus. I know I'm going to pull an I out. I know I have a negative 1 and 72. 72 is 2 times 36. 36 is 6 times 6. I'm liking that. So I can pull a 6 out. But I'm going to be left with my 2 on the inside, right? So I'm going to say I'm left with my 2 on the inside. I'm also left with my x on the inside. If you notice, we only have one x, so we can't make a pair. So that's why the x is on the inside there. And then don't forget, anytime we have a negative 1 inside that radical, we're just going to say that the square root is plus or minus 6 root 2x I. Anytime you're taking the square root of a negative, it will have an I. Pop quiz. What is I to the 11th? What's the nearest multiple of 4? I to the 8th times I cubed, because we need to get up to I to the 11th, 8 plus 3. So that's just 1. So this is just I cubed, which if we remember our pattern, I negative 1, negative I. There we go. All right. I want you to try this one. Pause the video. Think to yourself. These are pretty quick questions. Think to yourself, okay, I know it's a negative. I'll have an I. So I just need to break down the rest of it, just like we were before. Pause the video, try this, see what you get. And now that you paused it and unpaused it because you got your answer, I'm gonna go ahead. I know I have a negative 1 and 100. 100 is just 10 times 10. And that's a pair. So I can pull a 10 out. I'm not going to forget about my I, because I know it was negative inside there. X to the 7th. How many pairs can I pull out of 7? 2, 4, 6. Okay, so I have 3 pairs and then 1 extra. So I can pull 3 X's out. I'm going to have 1 extra X inside there. And I'm going to make sure to include my I at the end. Plus or minus 10x cubed root x, I. There's your next pop quiz. I to the 97th. So 80, I know 80 is a multiple of 4. 80, 84, 88, 92, 96. So I think 96 is my closest. This is I to the 96 times I to the 1st then. Any multiple of 4 is just 1, so 1 times I is just I. What if we had something like this? No square roots in sight. 3i times negative 4i times 2. Well, how are we going to do this? Let's multiply like we kind of normally would. Let's multiply the numbers. 3 times negative 4 is negative 12, times 2 is negative 24. And what about I times I? I squared. Doesn't look too bad. And I know something about I squared. What is I squared? Negative 1. And if you have to look back in your table right now, that's okay. But the two you really want to remember are I is just I squared is negative 1. Negative 24 times negative 1, positive 24. What about this? 4i quantity squared times 6i. Well, let's just do order of operations. Let's square the first part first. So 4i squared is going to be 16i squared times 6i. 16 times 6 is 96. You can use a calculator if you need. I squared times I is I cubed. But let's simplify that. 96 times what was I cubed? If you look in your table, it was negative I. So 96 times negative I this simplifies to negative 96i. Okay, yay imaginary numbers. They're kind of cool, they're kind of stretching your brain. Your brain might be hurting right now. But why are they in this unit with quadratics? Well, now we could solve something like this. Check it out. 3x squared plus 27 equals 0. Not too bad. If I'm solving, and I just have x's in one term, I just have that x squared, I'm tempted to just get it alone. 3x squared equals negative 27. Divide by 3 on both sides, maybe. So x squared equals negative 9. And here's where the light bulb might be going off. Before today, we would have been sunk. We said, we can't take the square root of a negative. There's no such thing. We know better now. Square root of x squared is x. Square root of negative 9 is plus or minus 3i. And how did I get that so quickly? Because square root of negative 9 is just negative 1 and 9, and 3 and 3. So the square root of 9 is 3. The square root of negative 9 is 3i, plus or minus on both cases. Square root of a negative number is just the square root of the positive number version of that number times I. Square root of negative 9 plus or minus 3i. Let's do one more and then we'll call it good for today. 4x squared plus 64 equals 0. Let's do the same thing. 4x squared equals negative 64. Divide both by 4. X squared equals negative 16. And if I take the square root, x equals plus or minus, always. Square root of negative 16 is going to be square root of positive 16 I. Plus or minus 4i. Because square root of positive 16 would have been 4, but it was negative, so we have to put the I on there. This is typically where we start really stretching ourselves, stretching our brains. You've also heard me say, and maybe other people say sometimes, oh, there's no real solution. There's no real solution. Well, great, what does that even mean? And I've kind of sidestepped that question in the past, but what that means is, if we had a parabola like this, there is no real solution. It never hits the x-axis. But there might be imaginary solutions. There might be complex solutions. And so that's what we were introducing this for. Guys, this was the first half of 5.4. We're going to take one more video, one more day to look at the other half. But right now, you're going to have some practice problems just on these imaginary number basics. It's not easy. It's not easy adapting and figuring out this kind of new form of math. But I'm hoping this made sense. Again, in a video format, you can pause, you can rewind, you can watch it as many times as you need. Hopefully my explanations helped out a little bit. If you have questions that you've watched the video a couple times, you still can't figure out, just write them down so that you can ask me next time we meet. But until then, have fun. Welcome to a whole new world of imaginary and complex numbers.